This meeting is being recorded.
Hello, my name is Ralph Weber. I am the Western Digital Representative to the SCSI and ATA standards committees that work mostly on the interface standards between hard disk drives and hosts. For 25 years, I worked on the SCSI primary commands standard. That's part of a 40-year career on hard drive interface standards overall. And this is as opposed to solid state storage standards, although those are represented in particularly SCSI and ATA to a lesser extent. The problem is that there are differences between the two that actually matter for this talk. Prior to working on the standards for HDD interfaces, I was the maintainer for the disk class driver in the VAX VMS operating system. The issue that I want to discuss today is in fact queuing inside an HDD and its relationship to cloud configurations. And queuing in an HDD is a much more serious issue than queuing in an SSD because the HDD contains a head armature that is essentially a schedulable resource. And in fact, the quality of the scheduling of that resource has a great deal to do with the performance of the HDD. Right? But what we've observed from a modeling point of view over the course of the last few years is that the HDD in a cloud cannot act in the traditional form for queuing that has been in place for several decades. The queuing that we've been using for these several decades assumes that the HDD is a sole actor, does its own work, and the efficiency with which it does its work is the only thing that's important. In a cloud, the HDD is acting as a service that probably is mirrored on multiple other HDDs, perhaps in far-flung locations around the world, and in reality, from the cloud application perspective, the behavior of that collection of HDDs is the queuing entity that matters. And we need to do something about the way the interface to HDDs is standardized so that the HDDs can do a better job of being team players in that larger queuing model. The situation goes back to the very classic observation that read performance in terms of total IOPS is greatly improved by increasing the queue depth, which is the graph here. Right? The problem with this classic picture is that there's another metric that makes a big difference in a cloud environment, and it's tail latency. In the worst case, the case where tail latency is induced by read retries, we've already added the fast fail concept developed by OCP so that read commands that are taking too long because they're doing retries can be terminated and allow the drive to go on to do useful work. The notion being that the command was satisfied on some other HDD somewhere that didn't have a read retry problem. But in the case for today's discussion, we're interested in the average tail latency. And the graph here shows that even for the average tail latency that does not arise from read retries, the more commands you put in the drive, the greater the tail latency. And the cloud vendors realized this some time ago and implemented their own solution. Starting from the graph that we showed on the previous slide, we have an unconstrained HDD which has in it as many commands as it possibly can have. And you see that the IOPS are great, 250 IOPS, but the tail latency is 677 milliseconds. What the cloud vendors did to solve their problem was they constrained the number of commands that they put into the drive, sometimes as low as 1, which is the use case we've done here, which would produce a tail latency of 12 milliseconds best case. And the cloud vendors keep the other 31 commands in the host and dole commands out to the drive on a one-by-one basis. And when this is done, the IOPS crash to 82, okay, and the tail latency, however, does improve to a 390 milliseconds number. What we're trying to do with the work at hand is to somehow optimize this, to get all the commands back in the drive while keeping the tail latency down to the nominal case that the cloud vendors have observed, which is the 390 milliseconds number. From a standards point of view, we're going to do this by basically allowing the drive to see all the commands, but specifying that the drive will split the commands into 2 groups: traditional commands, that is, commands that receive the same kind of processing and queue depth behaviors that have been in place for decades, and sequestered commands, which have highly limited processing rules and don't represent an added load that drives up tail latency. Right. Now, because of the way the standard is organized, we want to get the commands transferred to the drive in the same way that they've always been transferred. And what that means is that there's kind of a ramp up. When the drive has no commands in it and it's the start of the day, the first, whatever magic number you specify, count of commands, goes immediately to traditional and they're processed as traditional. After that, what is presumed a steady state operation, each new command goes to the sequestered group and stays there for a period of time. Okay? Now, the period of time depends on when the number of commands that are traditional falls below the magic number. When too few traditional commands are around, something needs to move a sequestered command to be a traditional command. And there have been 2 models for how to do that out there. The very simple FIFO, first sequestered command ever received is the next command to go traditional, and some sort of command importance algorithm, which I'll mention again towards the end of the talk. That's in some ways one of the more confusing parts of the whole deal. There's an additional case that might make commands traditional, and that is that the host sends down a command and says, this command is traditional, I don't care. Put it in the traditional group right away. Now, that has an interesting side effect, and I'll get to it in a minute, but the thing I want to mention before going to that is the other special aspect of sequestered commands. Because the drive can see them, the drive now knows what it's going to take to process them. And if the drive finds a sequestered command that it can process in such a way that it does not affect the latency of the traditional commands that are there, then the drive is allowed to process that command. And that happens every once in a while, and it contributes to that increase in IOPS because it's a command that got processed faster than it would have otherwise. Okay. This whole sequestered command thing, aside from the big brush picture that I've drawn for you, is a work in progress. And this slide talks about the issues that we have in front of us, from easier to harder, as it turns out. How to limit the number of commands that are traditional, well, that's actually pretty easy. After all, the host already knows how many commands it's been sending in the previous world. So all it really needs to do is communicate that number to the drive. It's another field in a data structure somewhere, easy to standardize, not the kind of thing I'm really worried about. All right. But the rules about how the sequestered commands are able to affect traditional commands, that's a little bit more dicey in the sense that, well, from a starting point, somebody mentioned early on, you know, if a drive says that it thinks it can do a sequestered command for free, and it starts that sequestered command and finds that that command needs a retry, well, that's not for free anymore. And that command can't be completed. It basically gets exactly the little slice of time that it was supposed to get in the first place, and after that, it's still sequestered. Furthermore, the drive now knows that that command is sequestered, and it's probably not going to, that sequestered command is going to require a retry. So it's going to be more hesitant to try and process. It won't try to process a command out of the sequestered group at all, and it may it may take the most severe view of when that sequestered command gets to become traditional, in the hope that the fast fail mechanism will come along and pull that command out by aborting it. All right? So the other part of the rules for limiting the effect of sequestered commands on traditional commands effectively are a what-if case. What if for increasing the latency of the traditional commands by 0.1%, you could get 10 more sequestered commands per second? Okay. Would that be worth it? Is that a trade-off that's worthwhile? Right. And it's a what-if question, but it would seem that it might be good for the standard to allow for the host to say, okay, you can have this much leeway in taking those sequestered commands and doing them early. Now, the other thing is that we are pretty sure that hosts that are holding back commands today find occasionally that there's a command that they want to put at the front of the set that they're going to send to the drive. Well, that probably needs to be modeled in this interface, and that would basically mean sending a command that is marked in such a way that it goes immediately to traditional do not pass go, do not collect $200. And clearly, if there are some number of the right number of commands are already in traditional, and you add this one, you now have one too many. So the net effect of it is that after receiving one of these commands, 2 commands have to come out of the traditional group and be finished before the next sequestered command gets pulled. And that's why the wording is the maximum number of traditional commands as opposed to the only number of, that's why the wording is the number of traditional commands, and when you have you have a count that's below that, you go get a sequestered command, as opposed to wording it as a hard limit on the number of traditional commands. We also suspect, but haven't actually got strong proof, that there might be some hosts that want to force a command that was previously sequestered to immediately become traditional in the same way that they would be sending it down in some sense. Okay, and that is a standardese backflip kind of problem, because there's really no command-oriented way to do it. Okay, the closest I've come to in the terms of a design is to say, well, if that command, that sequestered command was going to get aborted, there'd be an abort command management function sent down to do it. Okay, and so what we would be looking at here is a equivalent management function that doesn't abort the command, but instead pushes it immediately to traditional, and that's the standardese backflip that's only worth doing if it's really needed. And we come back to the place where I have the most concerns, and that's the command importance. And the problem with command importance is that it's a very tempting thing to equate to priority. But having watched priority schemes come, be defined, and ignored for years, okay, I am not sanguine on the notion that priority is the thing to be thinking about. And the reason I believe that it's a problem is that priority is effectively in the eye of the beholder. So what we need to be developing as part of this effort is a way for the host to express what priority means to it, okay, so that the drive has some parametric things to use that can be set as different parameters by different hosts, so that each host can express its own view of priority in a way that the drive can implement in a consistent way across all host designs. It improves a whole lot of things. It means that we don't have to have specialized firmware that knows exactly what priority means for this customer. It means that we can test our firmware essentially as one body of firmware. We can bug fix our firmware and live confident in the knowledge that that bug fix will be good for all of our customers. And so this is one of the things that we are working on. There is actually some standardization in progress in the ATA group that points in this general direction. All right, so why are we here? We're here because we know that the project we're working on is something that, as a organization that is focused on building hard disk drives, we don't have the breadth of knowledge to do a fair discussion of what should the standard look like. Okay, we could talk to our various customers and we can apply our own choices among the various things that they say. Sometimes we may be able to satisfy all people at all times, but that's not something that's going to work out in the general case. We need to have an ongoing discussion between ourselves, the other hard drive manufacturers, and the cloud storage vendors to resolve what kind of rules really need to be fashioned for sequestered commands. What do we do in the overall sense, including the command preference choices, so that the cloud servers get the benefits of extending their concept of what a queue is into the drive. And if at all possible, we want to get this as close to right the first time as we can. This is easily the third or fifth priority / queuing management proposal that I have brought to a standards group. Most of them I've gotten approved. None of them do I see in widespread use in the industry, and it seems like a good time to try really hard to use the OCP storage group as a way to get a lot closer to the correct answer. Now, unfortunately, this also means a face-to-face meeting, which is either not legal at this time or won't be legal for a few, or became legal a few days ago, whatever. But we need a face-to-face meeting, and I'm hoping that this OCP storage working group can put that together sometime later this year, and I look forward to seeing all of you there and having a delightfully lively discussion. Thank you.
So these questions would come through the chat? Yes.
Is chat interesting?
There's nothing there right now.
Okay, yeah. Archon is turned on the chat. There's nothing there, and there's nothing in the formal Q&A.
Oh, there's Curtis. Curtis just asked a question. He wants to know how we're doing.
And David's asked us to explain what we think are our performance metrics. Okay, Patrick Harry has asked the question that the sequestration is considered differently from priority. And yeah, no, sequestration is about getting the commands that the host is holding back today into the drive, but with a sufficiently strong promise to go with it that when it gets in the drive, it will not contribute to outrageous tail latencies. So it's very much different from priority. It is affected by priority only if we choose to say, okay, something about priority is going to be how we pick what commands go from sequestered to traditional. And that's actually an option that's been on the table because there are people who say, let's keep it simple, and the only way you get out of sequestered is when you are the next in line to get out of sequestered. And you've been waiting essentially the longest. Does that help, Patrick? Hey, thanks.
So this proposal works hand in hand with the previous presentation by Facebook on QoS level priorities. They're very synergistic.
Ah, I'm glad. I was hoping we would do that. The structure that is already defined for deciding commands that are how commands are to be. Well, the thing that I talked about, the way for the drive, for the host to tell the drive what it means by priority, is already differentiated between reads and writes. So yes, there is a differentiation. It's not per se sequestration, though. The sequestration is a count. And Patrick is asking if the new duration features affect only the traditional queue. And the answer, as I see it, is that they most directly affect the traditional queue. But if we choose to use them as a way to make a choice about what to bring out from the sequestered queue into the traditional queue, then we've made that choice. Right? As a practical matter, it's a choice that hasn't been made yet, as I said. So this is a work in progress, and there's a fair amount of recognition that if we do it just the way we feel like doing it, we'll not have served the needs of people, and we need to have basically, I hate to say it, but a free-for-all, an open face-to-face discussion where this stuff gets bandied about without the time lags of written questions and so on. Yes, and David is asking if both reads and writes go into the sequestered. If there is a sequestered area, then it is essentially the order in which the command is received. If it's a read or a write, it still goes in the sequestered area either way. How it looks once it's in the sequestered area is a different question.
Yeah, and write commands have a much greater opportunity of being pulled out of the sequestered into the traditional quicker because they execute a lot faster and can be done between the read commands and the traditional without affecting them much more readily.
Bill's thinking about the cache.
Yeah, I mean they're going into protected cache. Yeah.
Yes, exactly. If they go into cache, then you can do them almost concurrently with the reads. I hadn't even thought of it that way, which is why we need to talk about it.
So just to extend a little bit on Patrick's question with regard to the duration features, so there's a single additional field that is going to be added, which is what the traditional queue depth is, and then the drive will take the commands and that traditional queue depth will be executed as normal as it is traditionally now, but then the host can give additional commands that will go into the sequestered queue while waiting to get into the traditional queue. So it's just an additional parameter that's added on to the interface.
Yeah, I read Patrick's question in a slightly different way because I know Patrick is right on the bleeding edge, and the most recent thing Patrick has seen happen in the real world is the addition of the command duration guideline to T13, SATA. And that is basically a guideline that is one of that set of parameters that we hope will help hosts describe their priorities to us without actually calling them priorities. So Patrick's question can be viewed. It can be what?
When we get to the sequestered queue concept, then an additional parameter is going to be added to that control log page, right? Yeah.
Yes, and some additional meaning could be given to the guideline as well. But the guideline is a very, very new thing that Patrick watched get incorporated or approved for incorporation a couple of weeks ago. So is that right? Is it a couple of weeks or a couple of months? It's not that long ago, though. Yeah, I thought that. Well, okay. I'm gonna do David Wheelock, who's got one in here between two of yours, Patrick. David is asking if the latency timing starts only when the sequestered command gets into the traditional queue. And that question, I think, depends on whether you're thinking of it in terms of fast fail or how the command is functioning. In the sequestered queue, in some sense, the command is waiting its turn, which it would have done effectively inside the host in another world. Okay. We actually haven't considered the answer to that question, but I believe that we have some hint at a value proposition for letting fast fail apply even in the sequestered area, since if we hit one of those read commands that does retries and isn't getting processed, fast failing that out would be a superior solution than trying to have the host guess at where the drive is and do it. Now, it may very well be that an interesting discussion needs to be held as to how fast fail does apply, but it seems to me, based on some of the cases I've thought of, that you'd really like fast fail to apply even to the commands in the sequestered queue. And
well, the
Patrick,
fast fail,
go ahead, Bill.
may be a little different. So if you have a command in the sequestered queue and you're going to try to opportunistically execute that between two traditional active queue commands, the implementation may choose to not do any retries on a sequestered command that's trying to be executed opportunistically, just so it doesn't affect the latency of the active commands. That command, if it does fail on the fly and needs a retry, that command is still in the sequestered queue. So when it gets finally into the traditional queue, it'll be executed as normal with the normal fast fail limits. That may be an implementation decision.
Well, it's certainly something we can discuss in the way the thing's standardized as well.
Yeah.
And yes, Patrick, I believe that we are trying really hard to do what Facebook wants. We've been watching the things that Facebook asked for, like more priorities and the more priorities than 2, which is the current SATA limit, and we've got it to the point where effectively there are 7 priorities, and the host gets to define what they mean, which is in some time. And one of the ways I like to think about that is if the host decides that priority 7 is the highest, and a different host decides that priority 1 is the highest, all they do is twiddle their parameters. The priority numbers are the priority numbers. They tell the drive what set of tools to use while executing the command. And that's how we get to the point where we have one set of firmware that works for everybody. I have no idea how we're doing on our presentation time limit.
Do we automatically get cut off?
I don't know.
So David asked a question about FUA. Operate as existing handle. We have 1 minute.
Oh, okay. We're trying desperately, David, not to change any of the way the basic commands work. So FUA would do what it does today. That, however, might be used as a reason not to pull it out of the sequestered queue. Okay.
Yeah, if it's a write FUA command, since it takes time to execute as opposed to just putting it in a protected cache, then it may not be pulled into the traditional queue and executed opportunistically. So
Thank you, Patrick. 1 minute. And so we're down to our last question probably at this pace. Thank you. Somebody's liking our presentation, Bill.
Yeah.
It's always good to have a fan in the house.
Okay, well, time to wrap up, Ralph.
Yeah, thank you for coming. Pay attention to the OCP storage reflector for information about possible upcoming face-to-face meetings on this topic. I have no idea. Curtis wants to know how many viewers. That's need to know, and I apparently don't need to know.
I think it said 40. There was 40 people listening.
Oh, is that? Okay.
Oh, 43. Yeah. Okay.
Okay.
Good audience. Thank you, everybody, for listening.
So